We present a novel approach to Bayesian inference of simulation parameters that leverages parallel differentiable simulators. In our domain of application, we compare trajectories of simulated observations against measurements from the physical system. Our goal is to find the posterior distribution over simulation parameters that result in trajectories that accurately reproduce the real observations. We use Stein Variational Gradient Descent, or SVGD, that is a Bayesian inference algorithm that uses particles to estimate non-parametric distributions. The simulation parameter distributions are often untractable, and the likelihood function over trajectories can be highly non-convex, as shown here for a parameter inference example where the two link lengths of a double pendulum need to be estimated from trajectories with 400 time steps. Local optimization algorithms can easily get stuck in poor local minima, while Monte Carlo approaches only slowly converge to accurate posterior distributions. To tackle this problem, we propose a new likelihood model particularly tailored for trajectory-based inference. We introduce the multiple shooting method, which splits up the trajectory into multiple windows and augments the parameter space by the start states of such shooting windows. As shown here, such multiple shooting likelihood over 10 shooting windows with 40 time steps each yields a significantly smoother optimization landscape, which particularly gradient-based approaches, such as SVGD, can leverage to approximate posterior distributions more efficiently. We introduce constrained optimization to SVGD via the modifier differential method of multipliers, which allows us to add equality constraints to the estimation process. For multiple shooting, we constrain the defects between the shooting windows to be zero. The defect is the difference between the last simulated state of the previous shooting window and the start state of the next one. With the addition of parameter limit constraints next to the defect constraints, we arrive at our algorithm, constrained SVGD. This estimation algorithm retains the accuracy of SVGD to approximate posterior distributions which yield closely matching simulations. Shown here is a comparison of the posteriors found by SVGD and other inference algorithms, namely a parallelized variant of the Markov chain Monte Carlo algorithm from the MC library, the cross-entropy method, stochastic gradient Langevin dynamics, and the no U-turn sampler. SVGD leverages the gradient of the log likelihood which it evaluates for all particles in parallel. We use code generation and a differentiable physics engine to efficiently compute such gradients in parallel on the GPU. In our first real data experiment, we evaluate CSVGD and the baselines on a dataset from a physical double pendulum. CSVGD is able to find a posterior distribution over the 11 simulation parameters that yield highly accurate simulations. These parameters generalize well to trajectories from a held-out test dataset with unseen initial conditions of the double pendulum. In our final experiment, we consider an underactuated mechanism where a robot arm with 7 degrees of freedom follows a prescribed motion while an acrylic box is attached to its end effector via a universal joint. Since the universal joint is unactuated and we cannot easily obtain its joint positions, we track the motion of the box through a Vicon motion capture system. We use 4 reference points as observations to compare simulated against real data. First, we estimate the inertia parameters of the box, as well as the friction coefficients of both degrees of freedom in the universal joint, via our method. We select the most likely simulation parameters out of the approximated particle distribution, which yields a close match against the ground truth simulation. Finally, we fix 2 500-gram weights to the bottom of the box and set up the estimation problem in a way that the 2 planar positions of both weights are to be estimated. This is a challenging problem since the parameters are symmetric. The dynamics are unaffected when the 2 weights swap locations. What influences the dynamics is when the weights are not aligned exactly opposite to each other inside the box, resulting in the entire box to tilt in a way that would significantly deviate from the observed motion. Our method is able to find a multimodal distribution over the weight locations that contains the observed real values. The lines connecting the particles visualize the symmetrical alignment of the 2 weights which was found by the estimation algorithm. Thank you for your attention.